Alright, now we're going to take a look at elastic collisions in one dimension. We looked previously at inelastic collisions, and we also were looking at those in one dimension. So when we look at conservation of momentum, there's a few things that I want to go over to make sure that everybody's on board with. And that is that we're looking really at collisions that happen in one dimension, which means that whether it's elastic or inelastic, all of the motion is happening along one line, which generally we call the x-axis. The next thing that we want to look at is the fact that we have two objects colliding, right? A lot of the times those two objects are big and kind of funky shaped when they collide. But what we do is we reduce those objects down into just their translational motion. In other words, we say that the two objects are very small and point-like when they collide. And so we're not getting the perfect answer here. We're getting the approximate answer, or the sum answer of their total motion, which means that we're using the spherical cow model of physics. So we are going to take a look at an elastic collision that happens between two small spherical cow objects that collide head-on, so that all the motion is one dimension along one line. So we look at these two objects and we're going to say, let's say they're billiard balls. So before the collision, you've got an object with mass A and velocity A, and an object with mass B and velocity B. After the collision, you're going to have the same mass for object A and some velocity that we don't know, that's a new velocity after the collision for object A, same mass for object B, and some velocity that we don't know for object B. Now, a few things to consider when we're taking a look at elastic collisions, and any collision in general, is the momentum is a vector. So oftentimes we have a sign positive or negative, and so we're going to assign some meaning in general every time we calculate these. We're going to say that any velocity value that's greater than 0, which would mean any velocity value with a positive integer, is going to be talking about direction to the right, and any velocity value less than 0 would be a negative integer, and we'd be talking about motion to the left. And this is true whether we're looking at elastic or inelastic collisions. So let's take a look. We know what conservation is for momentum, is that the initial mass of object and velocity of object, or the initial momentum of object A and the initial momentum of object B summed together, should be equal to the final momentum of object A and the final momentum of object B summed together. And that's going to be true for both the magnitude and the direction. And that's really important that we remember that both magnitude and direction are conserved quantities. We're going to assume in this situation that we have an elastic collision, which means that we're saying that the kinetic energy is conserved also throughout that collision, which means that the total of the kinetic energy of object A and B before the collision is conserved to the total sum of the kinetic energy for object A and B after the collision, where the individual kinetic energies may be different because the velocities are different, but the sum total is a conserved quantity. Remember that energy is not a vector. So when we talk about conservation of energy, that's scalar, so it's magnitude only. And for scalar quantities, positive and negative would be gained or lost. So, since we have two equations, momentum and kinetic energy, two equations is a system of equation. And if you have a system of equations, you can solve for two unknowns. And we've been doing this since we looked first at our kinematics. So that means that if we know the mass of an object the mass of the other object and the initial velocity of both of those objects, we can find two unknowns. We can find the final velocity of the first object and the final velocity of the second object. So let's take a look at how that's done, because not only is it a little bit neat, but it's also convenient to have that level of equation manipulation. So here we go. We're going to start with momentum, and we're going to rewrite it. So momentum, if I want to rewrite it so that all A values are on the right, so I want to move that over to the right, and all B values are on the left, I'm going to have to do some algebraic manipulation. But if I do that, then I can factor out the masses from the velocities. And if I do that, I factor out the masses from the velocities, I end up with this equation. MA distributed to the initial and final velocity, where it's initial minus final, and you can see that from up here that it becomes initial minus final. And MB distributed to the velocities, where here MB we can see that it's final minus initial because we moved the initial velocity over there. So here, this is still our momentum equation. Now let's take a look at our kinetic energy equation. Kinetic energy is conserved for an elastic collision. So we have initial energy sum and final energy sum for kinetic energy. And we're going to do the same. We're going to move A's over here and B's over here. And when we do that, we get 1/2 MA with VA squared minus VA prime squared equals 1/2 MB VB prime squared minus VB squared. So I'm going to bring you over here to see that. And what you're going to notice is that there's a striking similarity between the two equations, and you can get rid of the 1/2 term. So here we have the kinetic energy conservation equation rewritten so that it's in its parallel form to the momentum equation. So here's our kinetic energy equation, where the mass is distributed to the square of initial minus final velocity for A, and mass of object B is distributed to the square of final velocity minus initial velocity. And again, you see that it's the exact same pattern of final and initial velocity for A and B. So we have these two rewritten equations. And I want to remind you of an algebraic truth, something that you can remember from your beginning algebra classes, and that is that A squared minus B squared is going to be the exact same thing as factored out A minus B times A plus B. So we know that this is true. If you tested it out, if you distributed these two equations, you would get these values right here. So since you know that's true, you can apply it to the kinetic energy, and you can rewrite the equation, since both of them are A squared minus B squared. You can rewrite it as MA equals VA minus VA prime, we kept that consistent, times VA plus VA prime. And MB equals VB prime minus VB times VB prime plus VB. Right? This is still our kinetic energy equation right here. But what we're going to do is we have a system of equations, so we're going to combine them. And how we're combining them, instead of doing substitution, we're going to divide. Right? This is divided by, and we're going to divide it by our momentum equation, which if you write it so that the equal signs overlap, you could see that you've got MA on this side, MA on this side, MB on this side, MB on this side. So if we're dividing these equations by one another, those values are gone. You also have VA minus VA prime on this side, divided by VA minus VA prime on this side. So those variables are gone. And you get VB prime minus VB here, VB prime minus VB here. So those variables are gone. Once we're done canceling our variables, we get this equation right here, which says VA plus VA prime equals VB prime plus VB. This equation could be rearranged so that we have initial on one side and final on the other side, just like our other conservation laws. So then we'd get VA minus VB equals VB minus VA. And that's really interesting because that's really just saying that VA minus VB, or the velocities before the collision, are going to be equal and opposite to the velocities after the collision. So that's kind of neat because that means that the relative speed of the two objects in a head-on collision have the exact same magnitude but different directions, and that's regardless of mass. If you've got a perfectly elastic collision and these two objects come at each other and they collide, this is going to be equal to that but opposite in direction, right? That's going to have the same magnitude. So if that magnitude was 5, guess what? This magnitude is negative 5. If this magnitude was 6, then guess what? This magnitude here is going to be negative 6, or the opposite of 6. So since I have direction, let's establish this is moving to the right, so that's a positive. This is moving to the left, so that's a negative. That means that this value ends up being a negative, and this value ends up being a positive. So this equation says regardless of mass, when two objects collide with each other in a head-on collision with the same magnitude, their velocities will have equal magnitudes and different directions. This is really nice, and what you could do is once you derive this equation, you can remember it, or you can rederive it. And if you can remember this equation, remember it's not given to you on the equation sheet, then you can use this in place of the kinetic energy conservation, because kinetic energy has squares in it, right? 1/2 mv squared. Whereas this equation here, VA minus VB equals negative VA prime minus VB prime. All right, no squares, no masses. All right, compare the two. No squares, no masses. This is going to be much simpler to use. But it's important. You either need to derive it yourself, right? This is how you do it. You derive it yourself, or you're going to have to somehow commit this to memory. There's nothing wrong with committing it to memory because it is a pretty straightforward concept. It's saying that in a perfectly elastic collision, the velocities will maintain magnitude but reverse directions regardless of mass. It's a pretty easy to remember concept that's represented mathematically in this form. But all you have to do is remember that that is always going to be true. So let's take a look at some calculations that we can use now that use this conservation of energy and conservation of momentum concept. So our first example is going to be example 7.7, and we're going to be taking a look at two billiard balls colliding. So two billiard balls. The nice thing about billiard balls is that the mass of object A and the mass of object B are going to be the same because the billiard balls are going to be the same mass. Another thing that we're going to take a look at is the first billiard ball is in motion. The second billiard ball is at rest. So this is actually VB equals 0. That's important because we're going to be needing to find the final velocity for object A and B after a perfectly elastic collision. So since it's an elastic collision, we know that the momentum is conserved, and we know that kinetic energy is conserved. So now we're going to pull up, if we know that these two things are true, then we know that we're going to need a system of equations. Because we have two unknowns, VA prime and VB prime. So before the collision, MB is 0. After the collision, we don't know what VA and VB are, so we're going to solve for both of them. So let's go ahead and let's set up. First, we have our momentum equation. All right, initially, the momentum of object A is MAV, because I said VA equals V, and momentum of object B is 0. finally, momentum of object A is MAVA prime, and momentum of object B is MBVB prime. So if I set up my conservation equation, I get that MAV equals MAVA prime plus MBVB prime. And the nice thing about this equation is since MA equals MB, then I've got M, 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 since they're the same mass. Since the M's cancel out, since they're all the same mass, I get that the velocity is going to be equal to VA prime plus VB prime, which is really, really nice, because what I could do here is I can solve for one of those two variables. So I got this from momentum. And I also have from kinetic energy, I know that VA minus VB is going to be equal to VB prime minus VA prime. Right? They're going to be equal and opposite. So, one thing that I know is that VA equals V, so I can rewrite that equation. Oh, and VB equals 0, so I can write that V equals VB prime minus VA prime. So what I did there was VB is equal to 0, VA is equal to V. So now I have from kinetic energy, I have this equation, and I could set them equal to each other very easily, but then I would get obviously the equal opposite result. So what I'm going to do is I'm going to solve. Alright, since VA equals V and VB equals 0, and we could subtract from the momentum equation, and we get that V equals VA prime plus VB prime, and V equals VB prime minus VA prime, and I'm subtracting, so all my signs are flopped, and I get 0 equals 2VA prime. So if I get that, then that means that VA is going to equal 0. So if VA equals 0, and I can plug that back into either of the equations, then I get that V equals VB prime. So now I've solved it. I have that VA prime, the final velocity of object A, is 0, and the final velocity of object B is equal to the initial velocity that object A had. That is, that ball A got stopped by ball B, and ball B got the original velocity that ball A had. That shows that kinetic energy is conserved, as is momentum. And this is something that you can actually see all the time in pool. This occurs. The two balls, as long as they have equal mass and there's no spin given to the balls, because that changes, then we're not only looking at translational motion, then this happens very often, or very nearly often, where one pool ball hits the other. That stops the original pool ball, and the other one shoots off with very similar to the original velocity of the first one. And it's a strategy used by billiard players everywhere. So now let's take a look at something that will truly occur every time in a nuclear collision. So here we've got a proton, which has a mass of 1.01 AMU, or U, which is the Unified Atomic Mass Unit, and it's traveling with a velocity of 3.6 times 10 to the 4th meters per second. So it's really zooming. And it has an elastic head-on collision, as nuclear particles do, with helium. Helium is actually going to have an exact atomic mass of 4.00 atomic mass units, because it is 4 times larger than the proton. and its initial velocity is 0 because it's at rest. Now, we could change those atomic mass units into kilograms, but we're not going to need to because you have mass on both sides. Those units will take care of themselves. So we're going to assume that this collision takes place in almost perfectly empty space, and we're going to assume that this collision is perfectly elastic. So, since it's a perfectly elastic collision, we know that momentum is conserved, and we know that kinetic energy is conserved. So we're going to be using both of those equations to create a system of equations to solve for the final velocity of the proton and the final velocity of the helium atom. Now, one thing to note that's very different than before is that the masses are not the same, so the masses are not going to cancel from our momentum equation. Here, the momentum of the helium initially is 0, and the momentum of the proton is mPvP. So, we get that mPvP before the collision is going to be equal to mPvP after the collision plus mHeVhe after the collision, and that's given by these two values. And we also notice we can assume, because we've seen objects collide before, we can assume direction and confirm it mathematically. So now we have this equation, and we also can find, so this is our momentum equation. Now we can find our kinetic energy equation, which is regardless of mass, lucky us. So that means that Vp minus Vhe is going to equal Vhe prime minus Vp. And we can simplify it because the helium was initially at rest. So Vp equals Vhe minus prime minus Vp prime. So here's our system of equations, this one and this one. And of course, mass matters. So we can substitute this into our momentum equation. We can do that by saying that we're going to be replacing the velocity of the proton after the collision with this equation. So here we get mPvP equals mPvHe minus mPvP plus mHeV prime HE. And so what I did was I solved this Vp prime equals Vhe prime minus Vp. And then I plugged that in for Vp up here, and that's where I got these values right here. So, moving on, when I substitute that into the momentum equation, we can solve now because the only unknown is Vhe. So what we're going to do is we're going to combine like terms and we're going to solve for Vhe. So that's going to be Vhe is given by 2 mPvP, both known quantities, divided by mp plus mHe. And now we have 2 times 1.01 unified atomic mass unit times the velocity 3.60 times 10 to the 4th meters per second divided by the sum of the two masses 1.01 plus 4, or 5.01 units. And when we solve for that, our atomic mass units cancel out, so we didn't need to turn them into kilograms, and we end up getting a velocity for helium after collision of 1.45 times 10 to the 4th meters per second. And if we have that, we can plug it back into this equation, and we could get that Vp is going to equal Vhe prime minus Vp prime. So I had 3.60 times 10 to the 4th meters per second there equals 1.45 times 10 to the 4th meters per second minus VP prime. And I solve there, and I end up getting, sorry about that, I solve there, and I end up getting that VP prime is going to equal negative 2.15 times 10 to the 4th meters per second. So you can see this is a really convenient equation to know for kinetic energy because it makes it very simple to do substitutions. So the minus sign that we solved for the final velocity of the proton tells us that the proton did in fact reverse its direction like we intuited before. So we use the calculation to confirm our direction. This also tells us that the velocity of the helium is much less than the velocity of the proton initially, and that makes sense because the proton is only a quarter of the size of the original of the helium, and so that means that when it collides, it's going to collide and it's only going to transfer some of its energy. It's going to make it move much slower to conserve momentum. The lighter proton is going to bounce back from the helium nucleus, and it's going to be less than its original velocity, and the helium is going to move off, and it's going to have some mass, but its mass is going to be less. It's going to have some velocity, but its velocity will be less than that for the proton. So these answers, when you check them, what you do is you check them with your intuition. When two objects collide, one big and one small, the big one will gain some momentum and the small one will lose some momentum, but it will also bounce off and travel in a different direction.